go. Yeah.
I got my ticket for the long way round. 2 bottles of whiskey for the way. And I sure would like some.
Okay, yo, what are you doing?
Leaving tomorrow, what do you say? The cup song from Pitch Perfect.
Ah.
Yes.
Okay, Nigel. You gotta tell me.
What?
Why?
Okay, so I was down at the cricket club the other day.
Okay.
And let's just say there was an incident with a guy and a bat, and it was just
Wait.
okay.
Oh,
and
you
my leg,
broke. Oh, damn.
So normally, you know, I'd be at the gym, I'd be doing like those like 500-pound squats, because you know me, I'm pretty impressive.
Okay.
But now, like, I can't really use this leg. I normally do something at least with the other one, but like, I don't want to be imbalanced, right? Because it's all about looking perfect.
Okay.
So I just kind of did other stuff.
Really, Nigel? Really?
Well,
Okay.
it's hand-eye coordination, like cricket.
Okay,
well,
Nigel.
if you're the other, yes.
No, man, you gotta work out your other leg, so you get 70% of the benefit in your other leg. So there won't be any leg muscle atrophy.
To be completely honest, I don't really understand all this muscle stuff. So it's all kind of gibberish to me.
Okay, it's okay. We'll teach you.
Thank you. Yes.
On a minuscule scale, muscles, which may seem a pretty straightforward thing, are actually pretty complicated. They make up approximately 40% of our body weight and are necessary to everyday functions. Many different apparatus and components come together to make muscles function. Even something as simple as picking up a pencil or drinking a glass of water require many muscles and the components of each. First of all, the smallest strand of muscle fibers is called a sarcomere. Sarcomeres have the capacity to contract to 2/3 of their resting length as their Z-bands come closer together. This will be explained a bit more later. These sarcomeres bundled together form what is called a myofibril. These myofibrils, in turn, bundle together to form muscle fibers or cells. These muscle fibers bundle again to form what is called skeletal muscle.
To understand how a muscle contracts, you must first understand what causes a muscle to contract. Muscles contract due to nerve impulses or action potentials. Action potentials are waves of positive energy caused by the diffusion of potassium and sodium ions. This process of diffusion allows the wave of positive energy to travel from the brain through the spinal cord to the muscle so that it can stimulate contraction. This stimulation occurs at the neuromuscular junction, the union of the nervous system and the muscular system. This union consists of axon terminals, synaptic clefts, and muscle fibers. When the action potential reaches the axon terminal, it stimulates the release of acetylcholine into the synaptic cleft. The acetylcholine then binds to the muscle fiber, which causes the action potential to continue along the sarcolemma. As the action potential travels down the sarcolemma, it will reach a T-tubule and then go down said T-tubule. Here, the action potential stimulates IP3, which in turn stimulates the sarcoplasmic reticulum to release calcium.
Calcium is important to muscles as it enables their contraction. Calcium attaches to what is called troponin, which exists on a filament called the actin. Actin is one of 2 filaments that exist in a sarcomere. The thicker filament is shown here. This filament is called myosin. The thin filament shown here is called actin. To enable contraction of a sarcomere, globular heads must attach to myosin binding sites on the actin. But there's a catch. A thin band, which cannot just be moved at will, covers the myosin binding sites. This is called the tropomyosin. Now, think back to the troponin mentioned earlier. When troponin accepts the calcium, it causes the myosin binding sites to be uncovered as the troponin pulls the tropomyosin off of the binding sites. If the tropomyosin is not covering the myosin binding sites, the globular heads will always be attached to the binding sites.
When calcium is accepted by the troponin moves the tropomyosin away from the binding sites. Once the binding sites are open, the globular heads attach to the binding site immediately. The globular heads are able to attach as they are charged by the energy from ATP in the form of ADP and phosphate. Once the globular heads attach to the binding site on the actin or thin filament, the ADP and phosphate allow for the power stroke. The power stroke is when the globular heads bend or flex, causing the Z-bands to move closer together. Once the power stroke occurs, all the energy from the ATP is now used up. The globular heads are stuck in the actin. This is called the rigor state. The rigor state is when the globular heads remain attached to the actin and cannot unbind, causing the sarcomere to be contracted until the globular heads are able to unbind. The globular heads can only be unbound from the actin when ATP is binded to the globular heads. The energy from the ATP allows for the globular heads to unbind and also powers the calcium pump. The ATP is then split into ADP and phosphate and bound to the globular heads, giving them a charge, thus allowing the cycle to repeat.
You're gonna miss us when we're gone. Boom.